Oh, there he is.
Hello.
All right. Can people hear me? Sorry, I'm a
Loud and clear.
late. Loud and clear. Great. I was just at an interview with one of our provost candidates, so sorry I'm a minute late. Opening up chat. Yeah, thanks, Charles. We are at 19, so we're pretty close to everybody. Why don't we start to rock and roll then? Let me get my iPad here. Everybody in Southern Central California ready for the heat? We're supposed to start experiencing today and tomorrow. I know I'm not looking forward to it.
I'm ready for it to be like fall weather, like for real fall weather.
Yeah, me too. The leaves have started falling off our tree in our front yard, and so I'm like, oh yeah, it's that season. I'm looking forward to that. I'm with you. Okay, so you should see my iPad here. I've been having some technology problems today. Hopefully nothing more will happen. I wrote down some notes to start out. I finally made an assignment on the Canvas site for homework 5. That was the assignment I made last Thursday. I set it to be due tomorrow at midnight, so that gives you some time to ask questions today. And I sort of had planned to do that already. I want to remind you that when you turn in your homework, you can make other arrangements with me ahead of time too, but the preference is for you to upload a single PDF document. Don't take like 3 or 4 pictures or scans of your homework and upload 3 or 4 different documents. That's hard for me to grade. So please, if you can do it, upload a single PDF. If you can't, talk with me. Maybe I can help you figure something out. And then today we're going to finish talking about conditional probabilities. That's a topic I started last time. And then I'm going to spend a little time talking about Bayes' rule. The more I thought about this, the more interesting it began. So I think I'm going to go on to a little rant about Bayes' rule. And then I might get to start talking about distributions, but we'll definitely be talking about distributions next time. And then I think on Thursday, I'd like to just have a little quiz, like a 30-minute quiz on what we've talked about so far. So some conditional probabilities, some counting methods. So make sure that you have asked me your questions, and you've had a chance to get answers for them about the stuff we've been studying so far. Okay, is there anything on anybody's mind? Anybody want to bring up anything we should talk about before I launch into conditional probabilities? I'm trying to find the chat. Okay, nobody's throwing anything in the chat. Okay. So let me find my notes here. So we talked about conditional probabilities last time. So I'm not going to redefine what they are. But the idea is that you've got a random variable and it's got a sample space omega. And you have 2 events that are in your sample space. And we can talk about the probability that event F occurs given event F occurs. Okay. And then last time we said calculating that probability, it's the ratio of these 2 probabilities. Okay, so this is the formula for a conditional probability. And the idea behind a conditional probability is that when you've got an experiment and you've got a sample space, there's like a tree you can use to represent all the outcomes. You can't always do this, but a lot of times you can. And when you're talking about a conditional probability, If F is an event that you want to condition your calculation on, well, that event corresponds to some subtree. And E corresponds to some other subtree. And so the conditional probability is where they overlap. Okay. So conceptually, this is what's happening when we're calculating a conditional probability. And so if you think about the frequency definition of a probability as being the number of times an event occurs over the number of possible ways the event can occur, then this formula makes a lot of sense because, yeah, this translates almost directly into that same sort of frequentist formula for a probability. And we talked about that last time. But today I want to just work some examples of applying conditional probabilities. Any questions before I go any further? Are we all okay with this? I'm going to take a second and see if I can. Oh, there's the gallery. I want to make the gallery visible to me. Even though very few of you have your camera on, I can see that you're there. Or I can see that you're making me think you're there. All right, so let's do some examples. So the first one of my favorite types of examples, it's an urn and ball problem. So an urn contains 3 types of balls. It contains 10 white balls, 5 yellow balls, and 10 black balls. A ball is chosen at random from the urn. And it is noted, or we are told, that the ball is not black. What is the probability that the ball is yellow? Okay, so this is what we want to calculate. So oftentimes, one of the things that makes probability hard is that we have to turn a problem that's stated in terms of, verbal language, English language in this case. We need to turn that into a mathematical representation. So there's often not just one way to do that. So we need to be flexible. So here's how I did it. So I'm going to describe some events. Let me do these in a different color. Let B be the event that the ball chosen is black. Okay. But our ball isn't black. And so really what has just happened is the complement of B. Okay. The ball chosen is not black. I'm going to abbreviate black there for space. I'm going to say let Y be the event that the ball chosen is yellow. And what we're asked to calculate is what's the probability the ball that we choose is yellow when we know that the ball is not black. So this is the conditional probability that we're being asked to calculate. Okay. So the first thing you should always do is, well, can I apply the formula directly, immediately? And in this case, the formula would be the probability of Y intersect B complement over the probability of B complement. And so the numerator here is the probability that a ball is yellow and not black. And then the denominator is the probability that the ball is not black. And those seem to make sense to me. They seem reasonable, not impossible. So let me copy this and we'll move it over onto the next. We'll have to probably go back and look at, well, so this is what we want to calculate. So it's on the previous page, but we'll remember, I think there's 10 white balls, 5 yellow balls, and 10 black balls. Okay. So if I'm not black, then I'm white or yellow. So the probability that a ball drawn at random is not black is going to be, well, the number of ways I can draw a ball that's not black, that's 15, divided by the total number of ways I could draw a ball, and that's 25. Okay, so that's the probability that I draw a ball that's not black. So that's my denominator. So now let's look at the top, the probability that I draw a yellow ball and a ball that's not black. Well, yellow and not black, well, that's just going to be yellow. The set of balls that are not yellow or not black and are yellow are all the yellow balls. So what's the probability that I draw a yellow ball? Well, there's 5 ways for that to happen. And there's 25 possible outcomes. So here's our numerator. So this tells us the probability that our ball drawn as a yellow, if all we know is that it's not black, is 5/25 over 15/25. And now we'll simplify that. So dividing by a fraction is the same thing as multiplying by its reciprocal. So those 25s cancel, and then 5 goes into 15 3 times, and so that reduces to 1/3. So there's a probability of 1/3 that I withdraw a ball that's yellow if I know that the ball withdrawn is black or not black. And that's a condition. That's a straightforward conditional probability calculation. Any questions about that? I just repeat then that the trick is figuring out what events we need to play with. Okay, what events do we need to set up? And a lot of times it involves looking at the problem and identifying that last. What's the question you're focusing on? Okay, so here we know what's the probability that the ball is yellow. That's what we want to know. But then you look back and you see what we're conditioning that on. Okay, so let's do another problem. And so I'm going to ask you to help me set up some events. And so maybe I'm going to start on a new sheet. All right, so imagine there's a woman, Selena, and she's got to take some classes next semester. And she can't decide whether to take French or chemistry. Okay, so those are going to be her 2 courses, the 2 courses she needs to choose from. So what do we know? We know she prefers chem. Okay, but thinks, she only has a 50-50 chance of earning an A in chem. Okay. Oh, wait a second. I got that class wrong. I think she's got a 50-50 chance of earning an A in French. Okay. If she took chem, her chance of earning an A would be less let's say 1/3. All right, so here's what happens. She decides to flip a coin. Okay, heads, she takes chem. Tails, she takes French or something. Here's the question. What is the probability she gets an A in chem? All right, so this is the question we want to answer. What's the probability she gets an A in chemistry? So this is kind of convoluted. This isn't as straightforward a conditional probability problem as the previous one. So anybody want to propose an event that will help us understand how to calculate what we want to calculate? Charles, you still need me to go back for a second? I see you in chat.
So I'm not sure what event this would correspond to,
Okay,
but
I'm listening.
it seems like Daniel Rojas's suggestion should give us the correct answer.
Okay. Well, yeah, okay. You think it should give you the correct answer?
Just based on drawing a tree diagram.
Oh, drawing a tree diagram. Okay. So let's draw a tree diagram. So what would the tree diagram look like?
So it would the root would have two branches, French and Chem, with equal probability, and then on the French branch, it would have two branches with equal probability, but on the Chem branch, it would have one branch with the probability twice the other branch. And so we have A and not A for French. Both of those are 1 and 4. And then for Chem, we have A, which would be 1 in 6, and not A, which would be 1 in 3, or 2 in 6, because the French and Chem branches both had probabilities of 1/2.
Okay, so French, there's a 50-50 chance of getting an A, right? But she thinks, so she thinks she could earn an A with a 30% or 1/3 of the time in Chem. And then you're saying there's a half chance of taking either Chem or French because of the coin flip, right? And so just by looking at these 4 leaf nodes, it looks like the first leaf node has probability 1/3 of happening. The second one has probability 1/6. The third one has probability 1/4. And the fourth one has probability 1/4, just by doing the products, right? Because we're using the fundamental principle of counting, or rather, like the multiplication rule, right? Because what grade you earn is independent of the way of the class you chose. All right, so let's just double check. Does this work out? What's 1/3 plus 1/6 plus 1/4 plus 1/4? Does it equal 1? That's what I want to check first. So that you get a half here. What do we get over here? Well, this is 2/6 plus 1/6, and that's 3/6. So yep, that's good. That checks out. And so looking at the tree diagram, we're earning an A in chem. Let's pick another color. Oh, not green. Do purple. Earning an A in chem. That's this outcome, and that has probability 1/6. Okay. Yeah, I buy that. That would be convincing.
Could
Okay,
we
so-
say that first we have to take the first event saying we get chem, so then we say P of E conditional F would be like probability of getting an A after getting chemistry?
Well, let's not talk about conditional probabilities yet, because this tree diagram, we're not really thinking about it in terms of conditional probabilities. I mean, to the extent that we're restricting in a way to a branch, maybe you could make that case. But I think what Daniel is doing and what Patrick is advocating is looking at the tree diagram for the whole situation, and then just doing an analysis of all the options, all the leaf nodes, and looking at the probability for all of them, and then just making this conclusion that, hey, it's obvious from the tree diagram that the probability she gets an A in chem is 1/6. So this is almost divorced of, you can do this without conditional probabilities. I'm convinced. I didn't think about it this way, but I'm convinced you can do it. All right. Was that it? I didn't, it was that, who asked that question? Was it?
Oh, it was me, Daniel.
Is that
I was just
Daniel?
wondering if there was another way of doing it.
Yeah. So I'll show you the way that I was thinking about it that uses conditional probabilities. But yeah, this is perfectly good. And when I say good, I say convincing, right? A lot of times a professor wants you to do it her way or his way or whatever. Also, I'll show you the way I came up with, which is different. But this is convincing. Your job as a citizen, as a person, is to make a convincing argument, a clear, concise, convincing argument. And this tree does it. You know, there's a little bit of hand waving. There's a lot of stuff to say, but the tree does it. I'm convinced it can be made to work. But so consider this. Let A be the event that Selena earns an A. Okay. I'll put that in quotes so it doesn't look like an event. Let F be the event that Selena takes French. Well, actually, we're interested in chem, so I'll just do chem. Not French, chem. Okay, so we want to know what's the probability she gets an A in chem. So here, what's the probability that she gets an A and takes chemistry? So it's really, you can think of it like an intersection. Okay. So in the context of conditional probabilities, you can note that the probability that Selena gets an A, given that she takes chemistry, is the probability she gets an A and she took chemistry divided by the probability she took chemistry. All right. And so you can see our unknown, right? This is what the problem is asking. What's that? What's that probability? And so we can write the probability of A intersect C is the probability of A given C times the probability of C. And we know the probability of C is 1/2 from the coin flip. And then we also know that the probability she gets an A if she took chemistry is 1/3. And so you get 1/6. Okay, so there's the formula Daniel put into chat, right? The probability of those two outcomes. But here we're using this idea of conditional probability to get to that. And in the problem statement, I mean, what language is there in the problem statement to suggest there's a conditional probability? If she took chem, her chance of earning an A would be 1/3. So here you're seeing the probability of an A in chemistry is a third. And then you might look at this and say, what's the probability she gets an A in chem? You might say, oh, well, there's A intersect C, and there's A given C. And so if you see that you've got those two bits of information, maybe it'll lead you to think about their relationship using the conditional probability calculation. Okay. And a lot of times when you're doing math problems that are like this, where there's multiple ways to approach it, you got to do some scratch work. You got to write some things down, and you got to translate things into mathematical symbols to see maybe how to proceed. You got to play a little bit. You got to burn a little scratch paper, as it were. Any questions about that? Okay, so let me do another example that's based on a rule that we've seen before, but you'll see that our statistics textbook has a name for it. And so I'm going to use that name. I'm going to introduce it to you using that name. And I think they call it the law of total probability. And it's this idea. I'm going to draw a Venn diagram over here on the right-hand side, and then I'll continue writing on the left-hand side. So suppose this rectangle represents a sample space for a random variable. And suppose you have a neat way, or just some specific way, it doesn't have to have any particular properties, but you've got a way of dividing your sample space up into events. So I'm going to call this event A1, A2, A3, A4. And I'm drawing these events. These AIs have no overlap. And the collection of the AIs exhaust the sample space, right? And this is a fancy, nerdy way of saying the sample space can be written as the union of these AIs. And sometimes somebody might call these a partition of omega into events. So you have a way to divide omega into events. And then if you have some other event E, then E can always be written in terms of these other events AI. Okay, this is what the law of total probability says. So let me just get to the punch. So if A1, A2, A3, up to AN are mutually exclusive events, that means their intersections are empty. And if omega equals the union of the events, then for any event in omega, you can write the probability of that event equals the probability of that event intersected with A1 plus the probability of the event intersected with A2, all the way up to the plus the probability of that event intersected with AN. Okay. So this is the law of total probability. It lets you decompose an event in terms of other events that are mutually exclusive in a way that maybe the right-hand side here, it's a more complicated sum, but maybe each of these probabilities are each easier to compute. And so you can compute the probability of an event by decomposing it into easier sub-events. So over in my Venn diagram, oh, that's too hard to see. You can see these intersections. So E intersect A7, E intersect A6, E intersect A4. E intersect A5. And E doesn't have to intersect with everything, of course. So now let me add one thing onto this. Also, if the probability of AI is non-zero for all I, that index our sets AI, then we can say the following. The probability of B equals the probability of B given A1 times the probability of A1 plus the probability of B given A2 times the probability of A2 dot, dot, dot. Okay. So this expression, we're just rewriting this expression here using the formula we have for conditional probability. The probability of E, well, let me do it this way. The probability, oh, I used B's and not E's, so let me fix that. So the probability of E intersect AI is the probability, divided by the probability of AI is the probability of E given AI. Okay. So this is a formula that lets us compute conditional probabilities. If you multiply both sides by the probability of AI, you see that it is the same thing as that. Okay. And we'll use this version of the law of total probability when we talk about Bayes' rule. So it's important for us for Bayes' rule. But I'll give you an example of how we can use that just by itself. Okay. And the idea is, I'll repeat, if you have to calculate a probability of an event that's kind of complicated, maybe you can simplify it by choosing these AIs in the right way. Okay, so let me show you an example of that. All right. On social media. So I wanted to try to connect or create a word problem that seemed to have some relevance to today, but I couldn't find legitimate numbers out of any peer-reviewed paper or anything. So I kind of had to make some numbers up. So take this problem with a grain of salt. It's a fictional problem. On social media, content can be sponsored content or non-sponsored. It's the difference between paying for something or not paying for something to be posted. About 50% of sponsored content is biased in some way. About 30% of non-sponsored content is biased. If 10% of content on a social media platform is sponsored, what is the probability that a piece of content chosen at random is going to be biased? Okay. So with this information about content and sponsorship and bias, what's the probability that if you just pick up a piece of information or content from at random from a social media site, what's the probability that it's going to be biased? Okay. And I'll just say that this is sort of an example where our intuition starts to break down. It's kind of hard to figure out, to get a good gut feeling for what the probabilities are going to be. And I'll show you another example of where our intuition breaks down in a little bit. So let's just be careful. I'm going to let B be the event that the item is biased. Okay, so we want to calculate what's the probability of B. But this is a case where we want to break the content down into mutually exclusive pieces. And so I'm going to break it down into sponsored content and non-sponsored content. Okay. Let me do it this way. Item is sponsored, or item is not sponsored. So you can see that these two sets here, right, they're both subsets of all the possible content on a social media site. You can see that their intersection is empty because an item can't be both sponsored and not sponsored. Yeah, and they exhaust the whole sample space. That you take the union of these two things and you get every item on the content on the social media space. So these are going to be like our AI from the last definition, from the definition of the law of total probability. And what we're going to do is we're going to express the probability that our content is sponsored in terms of, or probability that, yeah, it's biased in terms of whether it's sponsored or not. So from the law of total probability, I'm going to write the probability of B is the probability of, yes, the probability that's biased. It is equal to the probability that's biased given it's sponsored times the probability it's sponsored plus the probability it's biased given it's not sponsored times the probability that it's not sponsored. All right, so what's the probability that a sponsored piece of content will be biased? It's 50%, I believe. And what's the probability that an item is sponsored? It's 10%. And the probability that a piece of content is biased if it's not sponsored, it's 30%. And the probability that a piece of content is not sponsored is 90%. All right, so multiplying this out, I get 0.05 plus 0. Did I do this right? Probability something's biased if it's not sponsored. Yeah. I think I get 0.27. Did I do that right? Or is it 0.
That's what I got.
Yeah. So you add these two things together and you get 0.32. So this calculation suggests that if you were to select in these contexts or in this circumstance, that a randomly chosen piece of social media content has almost a 1/3 chance of being biased. That's pretty remarkable. So this is an example of how the law of total probability can be used. Okay. Any questions about that? All right, so let's move on to Bayes' rule. So Bayes' rule is a deep and simple result. And it's a possessive Bayes rule. And so I'm going to write it down in a complicated way, and then I'll try to break it apart a little bit. So we're going to start with sets A1 through AN that are mutually exclusive and exhaust our sample space omega. Then the following is going to be true. The probability that event AI happens, I guess we have to have another event B. The probability that AI happens given event B happens is given by the following formula. So what I want to point out to you is what's going to happen is I'm going to reverse the order of these two. Okay. The probability that AI happens given B happens, I'm going to reverse their order, which you can't normally do. But Bayes' rule tells you how to do it. So my numerator is going to look like this. And the denominator is going to use the law of total probability. That should be a J. Okay, it's going to use the law of total probability and writes it that way. So what's happening here? The numerator is equal to that intersection, the probability of that intersection, and the denominator is equal to the probability of B. It's just written in a complicated way. Okay, it's written in a way that takes advantage of this element being part of a decomposition of omega that allows you to use the law of total, or the law of total probability. So let me just repeat that. The reason that Bayes' rule works is, on the one hand, you've got the formula for conditional probability. On the other hand, taking an intersection is symmetric. Oh, did I get that right? Yeah, I got that right. Okay, wait a second. I lost something. So we can write this. Okay. But this oh no, I'm screwing it up. Let me take another crack at this. This here is an expression of what's written in this formula. Okay. So this is a way to think about what's happening in that formula. So the reason that Bayes' rule works is by the formula for conditional response probability. You can write this. But intersections are symmetric, so you can write that. On the other hand, if you reverse the two, events in the conditional probability, you can write that. And so together, you get this cool relationship. That relates the two conditional probabilities. So I have just done something that my professors before me are guilty of, and that's I have made Bayes' rule really confusing. So I invite you to ignore what I did right here and just focus on the formula. Just focus on this formula, right? This is the formula for Bayes' rule. Why is it important? It's because it gives us a way to flip around these conditional probabilities. And I'll explain to you why this is so cool through examples. Okay. So you're free to ignore what I wrote here. Bayes' rule is deep, it's complicated, and I did not do Bayesians any favors by throwing this crap at you. So just forget about it if you like. Let me show you some examples, and then I'm going to tell you a little story. It'll be an incomplete story. It'll be a story to pique your interest and maybe encourage you to learn some more things about Bayesian statistics. All right, so here's a scenario. Here's a word problem. A certain disease, I don't have any particular disease in mind, affects 1 out of 10,000 people. A specific test for the disease is pretty good. And I'll tell you exactly what I mean by pretty good. Maybe that's too colloquial. I'm going to say it's not pretty good. It's quite accurate. Because in statistics and probability, we like to talk about precision and accuracy. So let's use those terms. It's quite accurate, meaning the following. So one of two statements I'm going to make. The probability that the test result is positive when a person doesn't have the disease is only 2%. And the second statement about its accuracy is this. The probability the test result is negative when a person does have the disease is only 1%. Okay. So suppose a randomly selected person gets the test and it comes back positive. All right. A randomly selected person gets the test and the test comes back positive. Here's the question. What's the probability that person has the disease? This is what we want to investigate. Now I hear my young self, my college age self say, well, isn't it obvious? Isn't the probability somewhere between 1% and 2%, right? The problem even says the test is accurate, right? Certainly the probability has to be around one of those. And I look to myself and I say, that's very cute. Thanks for sharing your opinion. Let's let the mathematics talk. Let's see what the mathematics says and see if the mathematics bears that out. Okay. And we'll use Bayes' rules to calculate that. So to do this, I am going to, so let me change to a gray color so we can distinguish between the problem statement and our work. I'm going to let D be the event that the person has the disease. And I'm going to let R be the event that the result is positive. Okay. So we want to know what's the probability that the person has the disease given the result is positive. Yes, young Jason, I hear you saying it's going to be about 1 or 2%. Okay, just hold your horses. Let's do the math. So I'm going to note that our event R is going to be part of the way we're going to partition the space, right? Because R union R complement, that's the result is either positive or it's negative, right? And you put those two together and you get the whole sample space. And if you look at their intersection, no test can be both positive and not positive at the same time. So this is how we're going to use Bayes' rule. And we're going to write Bayes' rule as follows. The probability of D given R is the probability, the probability of R given D, all right? This is the whole point of Bayes' rule, reversing the order of those events times the probability of D. And in the denominator, we're going to have the probability of R given D times the probability of D plus the probability of R complement given D times the probability of D complement. Oh, no, did I do that wrong? I did that wrong. Yeah, I did that way wrong. It's not the R's that we wanted to exhaust the space. It's the people that have the disease and the people that don't have the disease, right? They exhaust the space, and you can't both have the disease and not have the disease. So we're going to use the D's to partition our space. So we have P, the probability that you get a positive result and you don't have the disease times the probability you don't have the disease. All right, so let's write down what these probabilities are. Do we know what the probability is that you have a positive result if you have the disease? It's right here, right? So it's positive result given you have the disease. Oh, it's right here. So if you have the disease and it gives you a positive result, that's going to be result. That's going to happen 99% of the time, because 1% of the time it is negative. The test is negative. Okay, so let's just keep track of these. The probability that you get a positive result if you have the disease is 99%. What's the probability that you have the disease? Well, 1 out of 10,000 people have the disease. So a randomly selected person, the chance they have the disease is 1 over 10,000. So what's the probability that your result is positive and you don't have the disease? Well, that's the second case here. The probability that it's positive and you don't have the disease, that's 2%. And then what's the probability that you don't have the disease? That's 9,999 over 10,000. So we're going to take these numbers and plug them into the formula above. And we get something like 0.99 times 1 over 10,000 all over 0.99 times 1 over 10,000 plus 0.02 times 999 over 10,000. And if you multiply this out, you get 0.0049261108. All right, so the young me says, oh, that's a small number, right? This is much smaller than I thought it would be, right? It's less than half a percent chance. So let me let that sink in for you for a minute. This problem is talking about what's the probability you have a disease if your results came back positive, right? If the test tells you it's positive, what's the chance you have the disease, right? Young me should have said, oh, the chance is really high, right? If a test is positive, shouldn't that mean that you've got a really good chance of having the disease? Our calculations here tell you no. In this scenario, the probability that you have the disease, even though you tested positive, is tiny. Is tiny. Even though these numbers here make it sound like the test is really accurate, in truth, it's not very accurate. Well, it's not very predictive, right? It gets things right a lot, but in the end, it's not very predictive. And this is a good example of the type of probability that humans are not very good at. Okay, they're not very good at looking at numbers like this and deducing a counterintuitive results like this. So what's going on here? Anybody have a guess as to why this predictive power is so weak? Anybody want to throw
So if you
go ahead, Patrick.
If you imagine taking a person from the population, if you imagine instead of the test having the problem, we can equivalently imagine that it's a person will be of the 2% of the population where the test fails. So it seems much more likely that you're going to draw a bad test than that you're going to draw a sick person.
Oh, I see. You're saying that because these numbers, these accuracy rates are, even though they're low, it's more likely you get a bad test than you draw a sick person. That's an interesting way to think about it. And I think that gets at the way I've read about this and not the way I've thought about this, is that the disease is so much rarer than the error rates, that the error rates dominate in this kind of test, right? The error rates have a much higher probability of happening. The errors have a much higher probability of happening than you even getting a test. So that's kind of what Patrick was saying. Okay. So when you think about diseases and tests, and you see numbers like 1% and 2%, that shouldn't make you feel confident at all. What you really need to know is, how common is the disease? Okay, because that plays as much a role in the predictive power of a test as the accuracy of the test does. And these ideas are really important these days in the era of cancer testing and cancer treatments and genetic testing. Doctors really need to have their a firm grasp on statistics when they're talking with patients about prognoses with drug trials and whatnot. And sadly, lots of doctors don't have this kind of expertise. And medical schools are increasingly seeing the need to have doctors and candidates for medical doctor degrees as being more mathematically informed and mathematically trained. So you'll see that having math classes on your transcript probably makes it more likely that you'll get into a competitive medical school these days. So let's play with something just in this spirit. We've got how much? We've got 10 more minutes left. So let's talk about the SARS-CoV-2 virus. All right, it's the virus that causes COVID-19. So the presence of the virus varies in different areas of the country. Some people say that 1% of the people have it, and some people say 10% of the people have it. Some people say there's regions where there's 20% of the people that have it. But it's an unknown. Nobody knows how many people have it. Unlike the previous example where it said 1 out of 10,000 people have that disease. For COVID-19 or SARS-CoV-2, we don't know how many people, how prevalent the virus is in the population. There are two kind of tests that are out there. There's like, say, a saliva test, and there's like a PCR test. A PCR test is a genetic test. Well, maybe genetic isn't the right word. I've got bio majors in here. It's like a RNA test. And it's really accurate. Its false negative rates can range from 2 to 37%, but so those aren't great. But its false positive rate, they're really small, from 0.1 to 0.5%. So I want to ask the question, what's the probability you have COVID-19 if you take a test and get a positive result? So let's just play with that for a second. So let's let D be the event that you have COVID-19, and let R be the event that your result is positive. Then we can use Bayes' rule to say, well, the probability that you have the disease if you've got a positive test is the probability that you get a positive test if you have the disease times the probability that you have the disease, all divided by the probability you have a positive test and have the disease times the probability you have the disease plus the probability you have a disease, or you have a positive test but you don't have the disease times the probability you don't have the disease. So if we assume that tests are 98% accurate, right? That is the probability that you get a positive test if you have the disease is 98%, which seems pretty reasonable. And if we assume the probability that you have the disease, a randomly person selected from the population has the disease, say that's 2%. That's in line with seroprevalence across the nation. And then I guess what's the probability that you have a positive test if you are positive test result if you don't have the disease. Those tend to be very low, right? RNA tests, those are very low. So let's say like 0.5%. And then what's the probability you don't have the disease? Well, if 2% of people do have it, let's say 98% don't have it. Plug these into the formula down here. So 0.98 times 0.02 over 0.98 times 0.02 plus 0.005 times 0.98. You do this math and you get 0.8. So if you make these assumptions about how prevalent the virus is and how accurate your tests are, then if you get a positive test result, there's an 80% chance you've got the virus that causes COVID-19. This is why, if these are decent numbers, and I went to try to find numbers in the literature, if these are decent numbers, then this number explains why a lot of times if a person is sent to quarantine because they've got a positive test, they have to take 2 positive tests before they can demonstrate that they are free of the virus. Okay. So Bayes' rule is immediately relevant to us right now. And the good thing to know is that these RNA tests are pretty accurate. And if you want to waste an hour of an evening sometime, go and take a look at FDA documentation for different tests that are out there and see what their positivity rate is and what their negativity rate is. And what you'll see is that these rates are often couched in terms of different prevalence of the virus. Nobody knows what these numbers are. And so in the FDA documentation that these tests have to provide, you'll see that they've got different accuracy rates for different levels of the prevalence of the virus. And Bayes' rule is why. Bayes' rule is why they do that. Okay, I'm going to stop here. I'm going to do a couple more examples next time of Bayes' rule, or I'm going to do a screencast on it. I can't decide. I want to start talking about probability distributions soon next. So maybe I'll do a screencast on these things on the Bayes' rule examples. I want to move to probability distributions next and probability mass functions, density functions. I can't spell. And let me tell you what I want you to look for. Okay, there's some distributions we've talked about. Uniform distributions. Okay, we have those for both continuous functions and for discrete functions. I want you to make sure you read about Bernoulli trials. What the heck is a Bernoulli trial? And what's a good example of a Bernoulli trial? Okay, so read the text. Try to get an answer for that question. What's a Bernoulli trial? And Bernoulli trials lead us to what's called a binomial distribution. So see if you can figure out what a Bernoulli trial has to do with a binomial distribution. And binomial distributions will be really important for us. And you'll see these N choose K notations pop up when we talk about binomial distributions. And then some other distributions. There's an exponential distribution we've talked about. We'll talk about Poisson distribution. We'll talk about a normal distribution. And there's some others, but those are the 3 continuous distributions that we'll talk about probably starting next week. But on Thursday, we'll definitely talk about these discrete distributions. So as you read and you prepare for class on Thursday, take a look at those. Okay. All right, that's it. Thanks, everybody. I will see you in office hours, student hours, and I will see you online. Okay. Stay well, stay safe. See
I
you
have a
Thursday.
question.
Yeah.
Actually, I just realized that my email never went through. I spelled it wrong.
Okay.
It's just where are the recordings of the lectures saved? Because I wanted to look back at a couple of them.
Okay. So let me show you where they are. Let me open a web browser. There is a little trick, so don't feel bad that you're a little confused by them. So I've got a browser opening. I'm going to share it now. And I'm just going to land on our page as if I can look at it as if I'm you. So here's what you should see when you come to our Canvas page.
Okay.
What I want you to do is you click on pages, and then you come up to view all pages.
Mm-hmm.
And then links to course material. That's where all the stuff you want to review is. So you can link to course material. And I've got a table right here. Okay. And it's got a column with links to the video recordings. And it's got a column with links to the lecture notes. And then when I've shared an R script or something in class, I try to put them here as well. And I put a copy in the files portion of the Canvas site too. But this is what you're asking for.
Yeah.
Okay. And
all right, great. Thank you.
Just so everybody knows, recently I started, the early links go to Zoom itself. And so you watch the recording of the lecture through Zoom. But for technical reasons, I've started recording things off my computer. And so the last couple links are to the full movie on Google Drive. And there's also a copy there to a YouTube version of it. So just so people know, there's a switch in the way I'm sharing these videos. Somebody wanted to ask a question. Ashley, was it you?
Yeah. When you click on the lecture notes, at least for me, it takes me to a Google access denied. And like, even if I make sure it's on my school account, it won't let me access it. I just get the access denied.
Even when you know that you're authenticated to your CI account, you get an access denied. Okay, let me make a note to look at that right now. I should be able to change that. So Math 352 lecture notes. Permissions. So I'll change that, Ashley, and then I'll send you an email so you can check to see if it works. If the change I made any difference.
Awesome, thank you.
Is it any one of these lecture notes or?
It was any of the Google ones I've been having a problem with.
Any of the Google ones, because the first three I think are on Canvas. Okay. Very good. I'll fix that right now.
Thank you.
You bet. Anybody else have any questions for me?
Which chapter are we reading again before Thursday?
There is a chapter in the free PDF that's called distributions, I think. Let me open up my PDF of it. And so I can, chapter 5, distributions and densities. Okay, so you can just focus on 5.1. Those are for the discrete random variables. And we'll talk a little bit about the densities later.
Okay, thank you.
You're welcome. Thank you for the question. Anything else from everybody? Okay, very good. See you all on Thursday.
Bye, Dr. Miller.
Bye-bye.